In this video, we'll be learning about color models that we always use in computer graphics. In the beginning, we will be discussing about some of the properties of light or some aspects of light and colors. And we'll then look at RGB color model and CMY color model. And at the end, we will see how CMY to RGB and RGB to CMY transformations can be done. So we all know that the visible light, what we see, is composition of the various colors, that is VIBGYR, and so we can say that this color is also part of a electromagnetic spectrum, and especially in the visible band, the frequency band of the visible light also contains, or basically we can say the colors have a frequency band with respect to some frequencies with respect to the electromagnetic spectrum. Right now, in the visible spectrum, the higher the frequency, the most higher frequency is the violet color, and the lower frequency is red color. So from the higher frequency, that is from violet color, to the lower frequency, if we travel, we get to see light from the lights of the colors of VIBGYR, from higher frequency to lower frequency. Now you see, the reason why we see color is because the source emits the light and the surface reflects the light. Right now, what happens is, be it a sunlight or a light that you have in your room, or any of this light which produces white light, actually have all of these visible colors in them. Right now, how do we see colors? When white light, or basically a light of any color, or light which is composition of multiple colors, hits on a surface, this surface reflects the light back. So it will reflect some portion of the light back, and it absorbs some portion of the light. So basically, whenever the light hits on a opaque surface, say a white light hits on an opaque surface, and this light, this surface absorbs all the frequencies, but the lower frequencies is not absorbed, but every frequency in the higher band of the frequency bandwidth is absorbed. Then the lower bandwidth, that is lower frequency, that is the red shade or red light, or the composition of the light towards the red in the frequency spectrum, is reflected back. It might be yellow or orange or reddish shade. Right? All other color components will be absorbed by this surface. So that's how we get to see the color, and we get to see the color because this reflected light hits our eye. Now, say the white light is reflected back, meaning to say the light is hit on a surface and all the color components are reflected. Right? Then this is the depiction of it. If you see, all color components are almost at the same level. So the mixture of all these colors is the white, and that is it. The surface has not absorbed anything or any particular frequency, because of which the white is reflected back and you get to see the white. Now let us say the white light is hit and some component of red shade is reflected back. Then that means that, this frequency towards the red side is reflected back, and some amount of other colors are reflected back. So the material or the surface will look or will appear in the shade of red. Why I am saying it will be in a shade of red but not red is because if you see here, this much component is contributing the whiteness, right? Now let us say that the surface will receive some white light and it reflects the complete red light and all the other color components are absorbed. All other frequencies are absorbed. In that case, this surface will look the surface which reflects red like this will appear in complete or pure red color, right? So say suppose this surface, instead of reflecting only red, it reflects some amount of red and some amount of green and absorbs everything else, then we see the shade of yellow or orange shade, which is a mix of red and green basically, right? Say in a room, if you have two lights, one is a red light and other is a yellow light, then if you give switch on them and let us say you can control the intensity of these lights, the green light and the red light in the room, right? If you switch on the light and turn it on to the full intensity, then everything the room appears to be more yellowish in nature, because the yellow light is what is in the red and the green light mixes up and yellow component gets reflected back, or yellow light is predominant in the room. It's basically, say, yellow light and green light and red light comes and hits on a surface, and that surface reflects both of them back, then the surface will look yellow. So that's the whole idea, what I was saying. Now say suppose that a surface reflects something predominantly, then this light, the light which we perceive because of this reflection, is actually called as dominant frequency. In this example, the red is dominant frequency. Even in this example, red is dominant frequency because we are getting to see some shade of red, right? Now this dominant frequency is also called as hue, or we can generally say it as the color of the light. Now, given any context, if we have a method which lets us to explain behavior of color in that context, then such method we can call it as a color model, right? Now you see, in the previous example where I told if in a light I have a green light and a red light, then I can if both of these lights are falling on a surface at the equal intensity and full intensity, then I will see the surface, if both of them are reflected back, I will see the surface as yellow, right? Now let us say I control the green light component, or basically I reduce the intensity of green light, and in that case the surface will receive more of red light and less of green light, right? And both of them are mixed together, but the red component is more. So what you see is a shade of yellow, probably something like an orange. So what I am essentially saying is we can use these color components to mix with various intensity levels or various amount. It's like take a paint artist, he can take two pure colors and he can mix those pure colors with different proportion and get to generate different colors, right? So something like that. You can control the intensity of these two prime colors that you have in the scene, that is in the room, that is the red color and the green color. Changing the intensity will give you a wide variety of or some different shades of colors, that you can achieve in the frequency band between the red and the green. Now in this context, this red light and the green light, we call them as these two are the predominant dominant frequency that we have. These two are called as primary colors in my setup, right? Now the most common primary color we use, or we most of us know, is the RGB, because using RGB we can perceive almost all the colors that we get to see in the visible spectrum. Now you see, using RGB, by taking the red color, green color, or taking the red color and blue color, or mix and match them with different proportions, you get to produce wide variety of colors, right? All these colors that are produced using these primary colors are called as color gamut, right? Now this color gamut is basically a set of all these colors that the primary colors produce. Moving forward, we will see RGB model. In RGB model, the primary colors are red, green and blue. We can represent this color model using a unit cuboid like this. This unit cube is at the origin, the left bottom back origin. This point is at the origin of a coordinate system where the axes represent the primary colors. For example, let us say this axis represents the red color, this axis represents the green color, this axis represents the blue color, right? Then, assuming unit vectors in these directions, 1, 0, 0 coordinate position here gives us pure red color, or the red hue. 0, 1, 1, meaning to say absence of red, absence of blue, presence of green will produce us the pure green color. Similarly, 0, 0, 1 gives us pure blue color. The origin is 0, 0, 0, which means absence of red light, blue light and green light component will give us black color, and presence of all these three primary colors with full intensity 1, 1, 1 will produce us white color. Green and blue combined together will give a color which is also called as an secondary color or an alternative color model. It gives a color called as cyan, and blue and red combined together will give magenta, and green and yellow, as I discussed earlier, will give us yellow. Somewhere here we'll get the shade of yellow, and somewhere here we'll get the shade of cyan, and here we get the shade of, in this region, magenta. More bluish towards here, more reddish towards here. Now this is white and this is black. Along this diagonal connecting 1, 1, 1 to 0, 0, 0, we get grayscale. The gray towards the white side will be the lighter shade of the gray, and towards the black side will be the darker shade of the gray, and this position somewhere between is the center of the cube, and that will take 0.5, 0.5, 0.5 for RGB values, and it will give us the gray color which is the center of this diagonal that we are talking, right? Now imagine that this B, G and R represent unit vectors along these axes, or they represent pure hues of value 1, right, along this axis. Then the color that we get can be represented as the weighted sum of these primary colors. Meaning to say, let us say this R I set it to 0.5. This R I set it to 0.5. And this R I set it to 0.5. So if I set them to 0.5, 0.5, 0.5, so R is a unit vector. So half of this value is 0.5 of the red component, 0.5 of the green component, and 0.5 of the blue component will give us the gray color in the middle of this cube. Similarly, by changing the weights of this, we can control the amount of the corresponding primary color component in the color that we want. So if I want to produce something like magenta, then I will pass 101. So that means 1 into 1, the complete red color and complete blue color, and 0 into 1 of green, that is absence of green color, will give us magenta. So this color what we get here has complete blue component and complete red component. Let us say that if this is 0.1, then it has blue component. This line is this would be this point, right? It has slight red to it here, 0.1, and full of blue, so we get the color over here, which is at this spot in the cube. So this RGB color model, using this method of representing it using a unit color cube, we can model this RGB color model easily, or we can understand this RGB color model easily. Now this RGB color model is a additive color model, meaning to say the color models are basically can be differentiated into two ways. One thing is called as additive, the other one is called as subtractive. So what's the difference between them? Additive color model is a color model where in order to perceive a color, I will have to add the primary color, right? So if I have to see the red color, I will have to add the red color. Basically in this case, for additive color models, the background will be black. So an example where additive color is used is your CRT monitors. The screen will be black. In order to see red color, you will have to add red color to a pixel position. You will see red color. In order to see green color, you will have to add green color. So basically you should add the frequency what you need, that you keep adding the color that you want in order to get the primary color on the screen, right? So subtractive color model is where you basically have white color as your background. So if you are able to see the background as white color, that means the white light whatever is incident on that surface is actually reflecting back as it is, right? Now if you want to produce a primary color, you should subtract the incident light, should subtract the color component from the incident light. The surface, the color whatever you have on the surface should be able to subtract the color frequencies from the incident light and reflect some primary color or some color component back. So basically it will be subtracting the incident light and reflecting some portion of it, right? So that's the subtractive color model. The subtractive color model we use is usually the newspapers what we see. Newspapers usually have a background color. They use colors, they add colors onto the screen onto the paper, and those colors absorb some component of the natural light and reflect back some component which you will actually see from the surface and perceive the color. However, in CRT that's not the case. You put red color onto the CRT and you see red color. You don't have to subtract anything, right? And if you don't put anything, the absence of RGB will give us black, so you will see black anyway from the surface. However, absence of anything on the subtractive surface should give us white, because the white light whichever is incident on the surface will be reflecting back completely. So that's the basic difference between the additive model and the subtractive model. The color model, which this RGB color model, is basically a additive color model. Now coming up, we are going to see CMY color model. The CMY color model is a color model which uses three primaries, which are basically cyan, magenta and yellow, and it is a subtractive model. So as I said, in newspaper you actually use CMY color model. If you would have seen, I don't know if you noticed somewhere in your newspaper at the footer, you would have seen 4 dots of 4 different colors. An yellow color, something like a green shade, and something like something like a blue shade, and some shade of yellow, and some shade of grayish blue. Right. So basically, there are your CMY color dots: cyan, magenta, and yellow colors. So those will be the color dots which will be used. Those will be the colors which will be used for printing. Right. Now CMY, say suppose CMY also you can represent using a unit cube. Now you see, absence of cyan or magenta or yellow will have its background as white, right? So absence of these colors should reflect the complete light back. So you will have white color if the cyan or magenta or yellow are not there on the surface. Similarly, if you put the complete CMY, then you are supposed to get the black color. So 1, 1, 1 for CMY color model should give us black. 0, 0, 0, 0 for CMY color model should give us white. And the diagonal here will give us grayscale. Earlier in this case, from this 1, 1, 1 to 0, 0, 0, if we traverse, we were moving from lighter shade of gray to darker shade of gray. However, here we will be moving from darker shade of the gray to lighter shade of the gray if we traverse from 1, 1 point to 0, 0, 0. Right? Now you see, if you add cyan color to a place in a white paper, then let us say you want to see blue color, right? In that case, you add a cyan and magenta color component here. The white light which incidents at this point will reflect back only the blue component, and it will absorb the red and the green component, right? Cyan basically absorbs the red component, and magenta absorbs the green component, and what you will see will be the blue component. So that's how you actually get to see the primary colors RGB on the printing material, whichever is printed used in newspaper or your printers basically. Now you see, ideally when you use all of them together, right, you should see black 1, 1, 1, right? But typically when you mix cyan, magenta and yellow, especially in printing, when you mix these ink colors, then generally you tend to get shades of gray, not necessarily black. And we all know how much important black is in terms of printing, right? So what we do is, apart from having CMY color dots or color inkjets, we will also have one more dot, that is K. K is nothing but your black dot. So if we want black, instead of mixing C, M and Y, we can directly use the ink in the K directly to get the black. So CMYK is the general color model or color combination that printing uses, especially in print media, right? You actually don't see in the footer of a newspaper 3 dots, you actually see 4 dots. The first dot will be C, next will be M, next will be Y, and the last one will be K. So please go and look at your newspaper at your home. In some sheet which has color in it, at the bottom in the footer you will have 4 colored dots, right? So that will be C, M, Y and K. So that's about CMY color model. Moving forward, we will see how to transform CMY to RGB or RGB to CMY color representation. Let's say I have red, the RGB color, red 1, G1 and B1. If I have 1, 1, 1, so the color in RGB cube, when I have RGB value as 1, 1, 1 is white, right? Now for us in CMY color model, white is actually 0, 0, 0. So if I have 1, 1, 1 as RGB value, to transform that value into 0, 0, 0, what I'll do is I'll subtract the RGB value with 1. So the result what I will get will be 0, 0, 0. Similarly, let us say that I have black color, meaning to say RGB values will be 0, 0, 0. So if I subtract it with 1, 1, 1, then what I get will be 1, 1, 1, which actually represents black color in CMY. So similarly, you can change the weights of this RGB anywhere and you subtract it from 1, what you get will be the equivalent color in CMY color model. The same notion can be applied for transforming CMY into color RGB. So you can inverse CMY color into RGB by subtracting the CMY weights with 1, 1, 1, and the result what you get will be RGB colors. So this, guys, is about your transformation between CMY to RGB color models. Now if you see in OpenGL, most of all we have seen using GL color 3F to represent RGB primaries. Right, and we pass colors inside it, that is RGB value. So whatever values that I pass here is nothing but the weights of the color R component, weight of the color G component, and weight of the color B component that I want for my the surface on which I am trying to assign the color, or the pixel which I am trying to color. I'll give the color weights of RGB over here. I can give it 0.5, 0, 0. That will give me not pure red, but some shade of red, basically little lighter version of red. And if I use 0.1, 0, 0, I will get the whitish red or the very light red as my color for the pixel whichever I am trying to assign this color in my OpenGL. So that's one thing that we have to keep in mind, that the values that you give here is nothing but the weights that you represent in this equation. So that's all I have for you guys today. So that's about color models that we use in computer graphics. Thank you, guys.